Right, this is section 1.8 of Math 204 at the University of Wollongong. Now, in previous sections, 1.1, 1.2, 1.3, we've looked at basic operations, basic definitions, basic results for complex numbers. Sections 1.4, 1.5, 1.6, we're trying to introduce concepts needed for 1.7, which covers the fundamental theorem of algebra. Section 1.8 is trying to set up ideas for Chapter 2. So that's what it's trying to do. Now the first thing that's covered in here is inequalities. So what should I say? For all R and S an element of the real numbers, there are a couple of things we know about them. So we know that either R is strictly less than S, or S is strictly less than R, or R is equal to S. We know that if R is less than S, then that implies that minus S is less than minus R. And we also know that R greater than 0 and S greater than 0 implies that RS is also greater than 0. So there's an obvious question. Can we find an order on complex numbers that extends the order on the real numbers? That would be very nice. And we know that lots of other properties about the real numbers extend quite well to the complex numbers. The answer is no, and the rest of this lecture is going to be an attempt to try and justify that. So first of all, I'm going to tell you what a total order is. Wow, I'm going to tell you what an order is. Well, I'm going to tell you what a relation is. Okay. Okay. Let S be a set. A relation on S, a relation R on S, is a subset of S cross S. Okay. So I'm going to find a total order. Total order. A total order. There are a whole pile of different definitions associated to orders. I'm jumping straight to total order because we don't need any of the others. But go have a look at them on Wikipedia. Partial order, strict total order, a well ordering, lots of definitions. Anyway, a total order T on a set S is a relation so that, and I'm going to write it out one way, and then I'm going to write it a different way to make it clearer what I'm talking about. So A, B, and B, A, an element of T, implies that A is equal to B. 2. A, B, and B, C, an element of T, implies that A, C is in T. And the third property is that for all A and B in S, either BA is an element of T or AB is an element of T. So that's a total order. Okay, usually A, B inside the total order is written A is less than or equal to B, or occasionally when you have multiple orders on one set, multiple total orders on one set, occasionally A, T, B, where T kind of plays the role as the less than sign. But anyway, this is what I'm going to use. So rewriting the previous definitions, properties. So this is A less than or equal to B, and B less than or equal to A implies that B equals A, and this is called anti-symmetry. A less than or equal to B and B less than or equal to A, C, implies A is less than or equal to C, and this is called transitivity. And 3, for all A and B in C, either A is less than or equal to B or B is less than or equal to A. Okay, so an example. Standard order on R is a total order. I'll leave that for you to go check. Maybe I should give you a definition of what the standard order is. It can be defined by x, y, an element of R. X is less than or equal to y if and only if there exists u, an element of R plus union 0, so that x plus u equals y. Of course, then you need to define what the positive real numbers are, but at least that gives you some idea. Okay. Now this is an interesting result. Glenn talked a little bit about set axioms. He mentioned in the tutorial last time something called ZFC. Well, here's a result. Theorem. Every set has a total order. Proof. I'm going to hand wave really on this. I'm going to say the set of axioms ZFC imply this. Okay, so what's ZFC? Let's give a little more detail. These are called the Zermelo, Frankel axioms with the axiom of choice. And it is specifically the axiom of choice that implies the result. Some mathematicians don't like the axiom of choice, and they think it should be gotten rid of. And there's all sorts of people who try to work out what maths depends on it and what maths doesn't. Turns out every set having a total order depends on the axiom of choice. What is the axiom of choice? So this is one of those things that most mathematicians would take for granted. For any set x not equal to the empty set, there exists a function f from x into the union of x. So remember, when you're dealing with set theory, everything is a set. So in particular, the elements of x are sets themselves. And we can take the union of those elements. That's what this is. Union of the sets in X, so that f of A is an element of A. So no matter how big X is, it's possible to make a function that chooses an element from every set. So to put this another way, no matter how big X is, it is always possible to choose one element from each element of X. That's not very controversial when when X is not very big. So when X is finite, sure, pretty easy to do. When X is countable, yeah, sure, okay. When X gets a lot bigger than countability, that's when the questions come in about this. In any case, that's just a little background for you. Not testable. It's not going to be in the exam. It's not going to be in any of the assignments. Don't worry about it. But it's an interesting little thing that as you spend some more time doing mathematics, you'll see. So the axiom of choice means that every set has a total order. So an example. Lexicographic order. I've probably spelled that wrong. Right, so C, an element of C can map into R2, XY. Then we say that X plus, X plus IY is less than or equal to U plus IV if and only if X is less than or equal to U, or X equals U and Y is less than or equal to V. So this is, we apply the ordering on R on each of these components separately. This is the same as the alphabetical ordering. So on the letters of the alphabet, we have an order. A is first, A, B, C, D, E. And when you want to order all the words, you order them first by the first letter, then by the second letter, and so on and so forth. So lexicographic order is a way to define a total order on C when you already have an order on R, and it works more generally, of course, as well. Why am I going into so much detail about orders? Well, here's my claim. Of course, the claim I've already said is that we cannot generalize the order on R to C. So why? So we know that there's at least one total order on C. Okay, suppose that X and Y in an element of R. Now we know that if X is greater than 0 and Y is greater than 0, then this implies that X times Y is greater than 0. This says that multiplication behaves in a nice way with respect to the inequality. What happens in R? Sorry, what happens in C? Well, if I is greater than 0 element, then we should have I times, if I is greater than 0 and we have X and Y, X greater than 0 with X and Y inside the real numbers, if I is greater than 0 and X is greater than Y where Y and X are in the 0 numbers, then we should have times this by that, and we want to have the order on C to generalize the order on R, so we kind of want this to be true. then ix should be greater than iy, right? I is positive in some sense, and we want it to behave correctly with respect to multiplication, so when we multiply, this should be preserved and we get that. But then we can multiply by I again. I times ix is greater than I times iy, and of course that implies that minus x is greater than minus x. But x greater than y implies that minus x is less than minus y. This is a contradiction. Right, we have strictly less than, so they can't be equal to 0. It's a contradiction. So I greater than 0, wrong. Okay, well what about I less than 0? Well, then we would have ix is less than iy, and that implies that we times it by I again. ix is greater than, because we have less than, so we've multiplied once, flip the sign around, multiply again, flip the sign around the other way. Also a contradiction. So this leads to two things. So either I and 0 cannot be compared, while the property is preserved, or there is no total order on C that generalizes on R. So you either have to accept that you don't have a total order, or you don't have an order that generalizes the order on R. So that's what the notes are saying when you read through here. And that's what I mean by no. So we want to preserve this. We don't want to get rid of this. This is a very nice property of the real numbers. Which implies that we interpret what I've just done as saying that there is no total order on C that generalizes R. So if you care about R, no total orders on C. Okay, but we can make some statements. For all Z in C, the image of Z is in R, and the real part of Z is in R, and the modulus of Z is in R, and the argument of Z is in R. So even if we can't apply an order directly to Z, we can apply an order to the image of Z, the real part of Z, the modulus of Z, and the argument of Z. And this leads to inequalities where instead of talking about numbers bigger than or less than each other, we talk about regions in the plane. Right, so some examples. The set of elements in the complex numbers so that the modulus is less than 1. That's a really bad circle, but there you go. Circle at origin of radius 1. How do we show this? Well, we discussed it a little bit before. If z is equal to x plus iy, then the modulus of z is equal to the square root of x squared plus I squared. We know that that is less than 1, so that implies that x squared plus y squared is less than 1. And the dashed line here means don't include the edge. Here's another example. Elements of the complex numbers whose real part is less than 1. So the real part of z is equal to x, where z is equal to x plus iy. So there's our x, this is our iy, here's 1. We need the real part of z, yep, so x is less than 1, x is 1, so it's everything over here. Elements of the complex numbers so that z plus I is less than or equal to 3. So if z is equal to x plus iy, then the modulus of z plus I is equal to the square root x squared plus y plus 1 squared, which is less than or equal to 3. So we have x squared plus y plus 1 squared is less than or equal to 9. So this is, so the set is circle of radius 3 at 0 minus 1, which is equal to minus I. This is minus I. Radius 3. It's going to be 2I. And it's less than or equal to, so fill that in as well. And we have a solid line to indicate membership. Indicate membership. Okay. This is a very important example, so important that it has its own notation. NRZ. For complex numbers, put a Z0 there. Complex numbers, Z minus Z0 less than, strictly less than, R. So this is a circle of radius r at z0. It's called open ball. It's also called a neighborhood. Some people, well, the notes claim, some people call it an R neighborhood. Now, I haven't seen that notation much, but doesn't mean you shouldn't learn it. What's something like this that isn't open? So the set Z side of the complex numbers, the set of complex numbers, so that Z minus Z0 for some particular Z is less than or equal to R. So this is called a closed ball. Less than or equals, and this one is less than. Open, closed. Now these things actually have proper definitions, so let me give you the proper definitions of these things. Let S be a subset of the complex numbers. A point Z in S is an interior point if there exists a neighborhood centered at Z0, the neighborhood centered at Z0 contained in S. Or, another way to put this is that there exists R0 and Z0 contained in S containing Z. So there exists an R greater than 0 and a Z0 in C, so that Z is an element of the neighborhood about 0, and that is contained in S. A set S is open if every point is interior. So let S be a subset of C. The complement of S is the set. It's usually often denoted with a little denoted by a little c above. Complex numbers, set minus S, just the elements in the complex numbers, so that Z is not an element of S. And lastly, a set S is closed if S complement is open. Okay, let's return to this set here. So we have a point and we have let W be an element of this. So choose W over here. We need to find a neighborhood that contains W that's also contained in here. So W will have some distance from the origin, and so we know that the radius is r, and we know what w is. So we're going to let s equal z0 minus w, and from before we know that that is the length of this line here. I'm going to let let's say u stpq, yeah, we'll let u equal 1/2 of the minimum of z0 minus w, and the remaining portion, the absolute value of r minus z0 minus w. Then the neighborhood of radius u about w is contained in the neighborhood of about r of z0. Right? Because this distance is the distance between w and the center, and this distance is the distance from w to the edge, and 1/2 of that means that whatever the minimum is will fit inside. Since w is an element of r, z0 is arbitrary, every element of n r z0 is interior, and hence nr z0 is open, as claimed. Okay, now let's consider the set S equal to, and this was the closed ball that I mentioned, elements of Z in the complex numbers, so that Z minus Z0 is less than or equal to R. So this is some point, Z0, and we have some radius. And important to remember that points on the radius are in this set. So let's let W be on the edge. Okay, now, so Z0 minus W is equal to R. So for all u inside the positive numbers, there exists some element z, w, and let's say z inside the neighborhood about r of w, so that the distance from zw to z is greater than r. Right? This distance here is already r, so if I take any ball, I can always find a point that's just a little bit further along. So this implies that Z is not in S. So W is not an interior point. So S is not open. Not open is not the same thing as closed. I'll show you an example later on. Okay, so what is SC in this example? There's all the elements of Z in C, so that Z minus Z0 is strictly greater than R. everything outside of the circle. Choose W inside C so that Z0 minus W is greater than R, and choose U in R plus so that Z0 minus W is greater than R plus U. This implies that if Z is inside the neighborhood or about U of W, then Z0 minus Z is still greater than R. Right, so everything outside of the circle. Choose W an element of Z, so X0, and there's my circle, here's W. Then there exists U, positive numbers, so that the distance between X0 and W is R plus U. R plus U. Let Z be an element of the radius U over a half, W. Then Z0 minus Z is equal to Z0 minus W plus W minus Z. And here I'm using the so-called reverse triangle equality, which we have shown you in class. Absolute value of the modulus of Z0 minus W minus the absolute value of the modulus of this, which is greater than, well, that is R plus U minus U over a half, which equals R plus U over a half, which is strictly greater than R, which implies that Z is an element of, which implies that the neighborhood U over a half around W is inside the complement, which implies that W is interior. But W is arbitrary. I didn't. I picked any old W. Any old W. So every point in the complement is interior, which implies that S is closed. So it's not open and it's closed. There can be things that are not open and not closed as well. I'll show you some examples. Okay, so more examples. I won't go into so much detail proving these, and hopefully you've seen roughly how you can do it. Z in the complex numbers, so that the real part of Z is greater than 1 and less than 2. Now there's the real part, and there's the I times the imaginary part. There's 1, and it's greater than, so we don't include 1. And there's 2, don't include that, and it has to be in between. So that's a strip, horizontal strip. Here's another example. This is an important example. Z an element of the complex numbers so that the modulus is greater than 1 and less than 2. 2 minus 2. And again, I'm putting dotted lines because they're strict equalities. 1 minus 1, and it's everything in here. This is open. Any point in here, you can choose an appropriate neighborhood. The same goes that this is open. Any point in there, you can choose an appropriate neighborhood. Take the relevant distances and make sure you are less than that when you draw your neighborhood, and you'll be fine. What about this one? The real part of z minus I equals 2. This might take a little bit of effort. So let z equal x plus iy. Then z minus I is x plus iy minus 1. And the real part of z minus I equals x. So the set is, so z is in the set if and only if x equals 2. There's 2. This is a straight line. This is closed because any point away from the line has a minimum distance, and you can draw a neighborhood around it. Here's an example, z, which is similar to the closed ball from before. The modulus of z is less than or equal to 1. Elements on the boundary are included, as is the inside, so this is closed. Here's a more detailed example. Z inside the complex numbers, z minus I is greater than or equal to z plus I. So if z is equal to x plus iy, then we have x plus iy minus 1 is greater than or equal to x plus iy plus 1. So this is the same thing as saying that x squared plus y minus 1 squared is greater than, sorry, that should be an x squared plus y plus 1 squared. Square both sides, so this is x squared plus y minus 1 squared is greater than or equal to x squared plus y plus 1 squared. X's cancel. Expand these things out. X squared minus 2y plus 1 is greater than or equal to y squared plus 2y plus 1. So the y squareds cancel, as do the plus 1. Minus 2y is greater than or equal to 2y. So 0 has to be greater than or equal to 4y, which implies that 0 is greater than or equal to y. So this is not including, this is everything in there, not including the axis. And of course this is open. Another example. Complex numbers. Z squared plus z bar squared equals 3. So if z is x plus iy, then x squared is equal to, well, we wrote this down earlier, x squared minus y squared plus 2ixy, and x bar squared is x squared minus y squared minus 2ixy, and you can do the math, prove it. So x squared plus z bar x squared equals, well, the complex bits drop out. So you get 2x squared minus 2y squared is equal to 3, or x squared minus y squared equals 3 over 2, which gives square root 3 over square root 2 hyperbola minus square root 3 over square root 2. And of course this is closed by all the same arguments you've seen before. Z is an element of the complex numbers. 1 less than or equal to the real part of z less than 2. So if z is equal to x plus iy, then the real part of z is equal to x. So what's the graph look like? There's 1, and 1's included this time because it's less than or equal to, and there's 2. Now consider this set. If I take a point on here and I take its neighborhood, it will always intersect a point outside, so this is not interior. And that of course implies that the set is not open. What's the complement look like? So take a point here, take a neighborhood around it, it will always intersect the original set. So this is not interior, which implies that the complement is not open, which implies that the set is not closed. So z, an element of the complex numbers, 1 less than the real part of z, and strictly less than 2, is not open and not closed. So there are examples of sets, and open and closed are not perfectly opposite. They're not inverses of each other or duals or anything like that. They're not related quite like that. It's a little more subtle. Does require a little bit of thought, but once you get used to it, you'll see how it works. Z, an element of the complex numbers, modulus less than 1, and the principal argument less than or equal to, greater than or equal to pi over 4, negative pi over 4, or strictly less than pi over 4. Okay, so modulus is 1, and it's strictly less than, so we don't include the edge. Pi over minus 4 is there, and we do include that. And there's pi over 4 there. So that's everything in here. Same reasons as before. Not closed. And not open. Pages, huh? Here's another example. Z inside the complex numbers. The real part of z greater than 1, and the imaginary part of z less than or equal to 2. What does this look like? Yeah, there's 1 on the real axis, and we have to be greater than that, so we know we're working over on this side. And there's 2i, so strictly less than, but we know we have to be less than this, so let's put that in. I'm going to put an open circle there, because the point there will be strictly less than or equal to 2, but it won't be strictly greater than 1. So we're everything in here. And as before, not closed, and not open. And I mean, of course, very roughly you get the idea that where you have a less than or equal to sign, the edge is included, and that probably means that you're at least not open. And wherever you have a strictly greater than or equal to sign, the edge isn't included, and that may imply you're open, but it doesn't guarantee it, and you have to think things carefully. This is very important to know all these kind of things to do with sets in the next section, to do with limits and sums and sequences and series, which will be great, which is in chapter 2.